Okay. Hi everybody. My name is Alessio Trevisana and I am the Endurica product manager here at Enginsoft. As I said in previous webinars, I work in on offshore and construction department where I used to calculate special structures for that field of activity. And I found elastomer obviously on my path, and then I can tell you that it is a very hard challenge if you have no background or technology to understand them and to make right calculation. So I'm very happy in this context to introduce you Dr. Will Mars, that is a true expert on that field of activity. Dr. Mars founded the Endurica LLC in 2008 to give product developers a simple and accurate workflow for analyzing the durability of elastomer products. The firm's products and services are used by leading firms around the world to manage durability. And by the way, Dr. Mars has received several awards for his scientific contributions and innovations. He has more than 60 peer-reviewed publications, holds 4 patents in the area of elastomer durability, and is the past editor of 2 scientific journals. Today, he will explain us a very crucial topic that is capabilities and limits, what to expect from durability simulation of elastomer. So, without further hesitation, I give the floor to Will Mars. I will.
Hey, Alessio, thank you. Thank you for that introduction. And really excited to be here today and to have a chance to talk about what we can do and what we should expect. Sometimes, sometimes it's hard to sort fantasy from reality when people are talking about these things. But hopefully by the end of today, you'll go away with a really good sense for what is possible today and what is not when it comes to uh, uh, computing the durability of rubber parts. Let's see. Hopefully everyone can see my slides. I'll just say a few words about Endurica. So I'm the founder. I founded the company in 2008. We're based in Findlay, Ohio, in the United States. Findlay is about halfway between Akron, the rubber city, and Detroit, the motor city. So uh, we're right where you would expect something like this kind of enterprise to pop up. Um, what our real superpower is in providing a system that allows people to simulate the fatigue life of elastomers. And you can see here I've got a little movie that we did in ANSYS of one application. This is just a little micro jack, and of course we're interested in making sure that the insulation is going to be adequately durable in that application. Um, this is our current team. We're at about 10 people right now. Earlier this year, we announced opening an office in Europe. And so that's Wes and Jean-Pierre. And of course, we have our partner ecosystem, and we're really glad to be partnered with Enginsoft. They do a great job. So I want to start with this slide is kind of a shout out to the very first paper that was ever written about fatigue of rubber. The image, the photo there is a guy, Sidney Cadwell. He was a researcher who worked at what was called at the time the United States Rubber Company. Later it became B.F. Goodrich. Um, and But he published the very first paper on the fatigue life of rubber, and the quote that I just wanted to highlight here is his. They did some really nice work, but basically they were at the beginning of a very let's say steep climb, right? He said many theories can be devised to explain the way the dynamic fatigue properties of rubber vary with the strain and the strain oscillation limits, but such theories are still conjectures. And that was in 1940. Since then, of course, we've learned a lot about rubber fatigue, and if you look, there's just been a huge amount of work that's scientific work that's been done. Um, but it's a big field, and it kind of has a reputation because of rubber's nonlinearity, and because when you talk about fatigue or durability, you're really talking about very complex service conditions, right? In applications, a lot of times, so not only do you have the nonlinear behavior of the rubber, but you also have multi-axial loading, right? Load inputs from many directions. You have variable amplitude loading, um, and um, and there's time dependent effects and temperature effects and so on and so on and so on. So, metal fatigue has been around for a long time, obviously, but when you talk to people about rubber fatigue and what the expectation is, a lot of times the first reaction is, "Oh, that's hard." There's a lot of difficult issues. Can you really predict that? Um, so, um, so that's kind of the starting point for the rubber industry. If you've been paying attention to the news in the automotive industry, you know that simulation has become it's kind of taken the world by storm. Um, in fact, when I first started my career, uh, finite elements was just coming up as a commercial tool. And during my career, I've witnessed it go from being kind of a toy that people played around with in the research group to now being very much a central pillar of how people do product development. And if you want evidence of that, you don't have to look any further than many of the OEMs. This is a quote from a talk that one of the GM executives gave a few years back, and they said this was a talk he gave in 2021, so 4 years ago. But he said, with this is guy's name is Mike Anderson, but he said with virtual modeling, GM has reduced tooling and physical prototyping costs by 66%. That was as of 2021, which is a $6.5 billion cost savings. Um, and and their goal has been to have 100% virtual design capability by 2025. So in 2 months, right? To be there. So this, but clearly you can see why they want to do that, and that's a very important goal. So if you're a supplier, I'm sure that you're getting um, uh, pressure to do this. If you're on the OEM side, I'm sure that you're probably pushing your suppliers to be able to do this. So there's a lot of reasons to do that, and clearly they believe that it's possible, right? A realistic goal. Um, so and then so this is a picture of me at earlier this year here at Endurica. We had our very first in-person community meeting where we gathered. We had people from around the world come to Findlay, Ohio. We had talks. We actually scheduled it during a total eclipse, so we all were able to sort of experience a total eclipse. It was a lot of fun, but our theme for the conference was delivering durability across the rubber supply chain. Right, it's kind of responsive to this idea that the OEMs need a virtual capability. So that means people who make rubber parts need to be able to make these simulations and make those a part of their engineering process. And it means people who supply raw materials to the people who make parts need to be able to, uh, you know, work with these tools. Um, just a few more pictures. I just mentioned this event. Like I say, it's kind of a past event now, but we were really proud during the event to have a really great cross section of people from the OEMs, people from part makers, people from tire makers, people from raw materials, all in the same room, all focused on durability, and talking about what we can do uh, these days. So, again, I just mentioned this more as uh, news about what's kind of happening today in the industry. I would say that the industry in many ways is getting organized around. Um, in the past, we've always done a very experimental build and break process to qualify products for the durability requirements, but very rapidly, the industry is getting organized around using simulation tools to get these decisions right up front. Um, so, so that's kind of the background, and the question is so what should we expect in terms of these tools? And I'm going to organize my comments here. There's a lot of stuff we can talk about, but I want to organize my comments around three really core ideas: accuracy, completeness, and scalability. Right? If we're gonna bring these kinds of tools to and use them to actually deliver products, then first of all, the tools have to be accurate, right? We have to be able to make predictions that match reality. So all the things that rubber does that it's had a reputation for being hard, we really need to deal with that in a way that's accurate and true to life. And of course, there's a lot of smart people been working on this for a long time. So, um, uh, so that's not, let's say, a surprise or news. But it's actually not enough to have an accurate model. When you talk about durability, it's a very large space. And so there are a large number of issues that we need to deal with, right? Multi-axiality, variable amplitude. Um, there's different methods. And so completeness is also a really important idea. It's not enough to just be able to have a simulation that handles one kind of physical effect. We've got to handle the mechanical, the thermal, the chemical. Um, we've got different types of workflows. There are different experiments that we have to do. There's just a huge list of things. And so we need not only accuracy, but we need completeness of the tool set for the tasks that we need to complete. And then finally, scalability. So again, not enough to just be accurate, not enough to be complete, but these tools have to be scalable. So, whether sometimes we have small problems to work on, and we need a simple tool that I can afford and that I can use very rapidly. Other times we have huge problems where it's super important to be accurate, and so we need to be able to scale the tools from small to big and be able to do that rapidly. And so that's how I'm going to organize my comments today: is accuracy, completeness, and scalability. So first, let's talk about accuracy. Um, we've been doing a series. If you follow the EngineSoft Futurities magazine, we've been doing a series of articles with kind of the hook that rubber fatigue is not equal to metal fatigue. And we've been talking about many of the ways that rubber is different from metals and why uh, different differentiated methods are required. So we did one earlier this year on mean strain effects in rubber. We did another earlier this year of what you can do when linear superposition fails, right? If you're doing metal fatigue, sometimes people use a method called, scale and combine or unit load cases. And so we talked about methods for dealing with those types of, basically dealing with nonlinearity. And then very soon we're going to be also doing another one of these in the series on thermal effects in rubber. So these are all examples of aspects that it's important to get right when you're simulating a rubber part. Um, Talking about the mean strain effect, um, uh, this is a case study that was completed a number of years ago by one of our early users, Caterpillar, and they did a modeling study just on simple tension specimens, right? Rubber's behavior is so interesting that you can see weird things happening even if you just load in simple tension. Um, and uh, what they did was they compared the fatigue life of natural rubber versus uh, versus a synthetic styrene butadiene rubber. These are two materials. The natural rubber is an example of a rubber that strain crystallizes. SBR is an example of material that does not. And the Endurica code does provide you with material models for both types of materials. And you can get really, the strain crystallization can lead to very interesting effects. So the main point of this was that to the point where when you have strain crystallization, you can get cracks that we're accustomed to the idea that if I load in simple tension, cracks will appear perpendicular to the load, and that's true for materials that don't strain crystallize, right? So on the right, you can see the failed specimen for the synthetic material, and you can see we predicted a crack. The red is the predicted crack orientation and the specimen shows the actual crack orientation, and that we get that right, and that's easy to understand. What's more interesting is that when you have strain crystallization, it can cause cracks to appear in orientations that are not perpendicular to the load. And you can see that as an example here on the left. The red X is sort of indicating the predicted crack orientations, and of course the specimen is showing a crack at an angle. In the movie, if you look at the movie, you can see that the specimens are full of many cracks, some of which are, and they're all at these funny angles that we can predict with our crystallization model. So that's an example of one way in which the code is highly accurate for rubbery material. So, a lot of times people look at this and say, oh, it's very mysterious behavior, and it's like, no, we've got models and we can predict that. Um, if you again talking more about the mean strain effect, you can plot the mean strain effect out in the form of what's called a Hay diagram. So here I've plotted the Hay diagram for the non-crystallizing rubber on the left and for the crystallizing rubber on the right. You can see quite a big difference, right? So on a Hay diagram, the x-axis is the mean strain, the y-axis is the strain amplitude. The colors are indicating the fatigue life, where blue is long life, red is short life. And you can see when you have crystallization, there's a strong benefit for a certain range. If you increase the mean strain, there's a range within which the crystallized material actually improves the fatigue life by increasing the mean strain. Now, of course, there's a limit to that. If you keep increasing mean strain, the life gets short again. But the crystallization has an important effect on fatigue performance. And here I'm comparing this to published results out of France for experiments that were made on a rubber where they actually observed the mean strain effect on the Hay diagram. And if you look at the character of these are contours of equal fatigue life, the red lines that I'm showing on the image in the right. And if you compare those to the shape of our computed Hay diagram, they correspond very nicely. Again, an example of one way in which the code is accurate. Um, I mentioned thermal effects. This was a validation study that was done uh, in um, in China, and they modeled a solid cross section rubber wheel and used our code. The Endurica code does have a capability to calculate self-heating, right? Viscoelastic heating in the rubber, so you can calculate the temperature. And so this image just kind of summarizes that work. You can see they used an infrared camera to collect images of the tire running on this steel wheel. They used the Endurica code to calculate the temperature field, and you can see that the predictions are really quite good. They were able to get within 3% on the surface temperature prediction, and they were able to get not only do you get the temperature, but you also get the energy consumption of the system, and that they were able to get within 8% in this particular work. So again, speaking to the accuracy of the tools. Um, Endurica has a capability to model the effects of aging and oxidation on rubber. And so that's what you're looking at here is basically we're computing the Hay diagram for a strip of rubber that has had different exposures to aging. And what you see is the unaged material has a much larger Hay diagram. As the material ages, the envelope of allowable strains decreases because the material becomes more brittle and more susceptible to fatigue cracking. And so Endurica does offer an aging model that you can include as part of your simulation. Um, there's so many case studies that people have done over the years. This is year 16 for Endurica. But this is one that came out of Stellantis, where they, ran the models, ran the experiments, and made a careful comparison of prediction versus test. And you can see the results here. The CAE prediction was coming out as 520 repeats of a road load schedule. And when they went to the physical test, they got these four replicates that have an average of about 523 repeats. So quite good results. Again, speaking to the issue of accuracy. So, um, so it is quite possible, even under, complex loading scenarios. And I've got another example I'll show with a little bit more detail about how these things work. But that's some examples of ways in which the code can bring you accuracy. So let's talk about completeness now. When you say that you're going to work on durability for a part, you really need to specify what you mean by that. There's a number of different approaches that people take to durability problems. The four categories that we uh, normally see would be the infinite life, the safe life, the damage tolerant, and the fail-safe approaches, right? These are kind of well-known approaches that you can find in any fatigue textbook. Um, in the infinite life approach, we say that no damage is allowed. We just make sure that the loads are below the fatigue limit. So it's a very simple approach. Again, back to this idea of scalability. So if you don't have a lot of time or budget, this is an easy one to do. You just check and make sure your loads are below the fatigue threshold. You can calculate a safety factor S that indicates your margin of safety. Um, and that's a simple type of analysis we can do. Safe life is where your customer or maybe a regulation gives you a life target. In safe life analysis, we're operating above the fatigue threshold. And so we need to say, okay, I know I'm above the threshold, but how long can my part endure? And does that meet the requirement that I have? So in that case, we can run the safe life calculation. Endurica uses a fracture mechanics based approach, and we take the crack growth rate law. We assume that there's cracks of a particular size at the beginning of the problem, and we calculate how quickly those cracks grow until end of life, and that we can get so if you give me a load case, I can calculate repeats of that load case to predict the life of the part. That's what we call safe life approach. Now, sometimes in the safe life approach, you're assuming that some particular load case is just repeated to the end of life. But in real life, of course, every day is different. And so that's why we need a damage tolerant approach. And in the damage tolerant approach, we are monitoring and tracking the transient history of development of damage in the part. And there's no requirement that, it's not a matter of repeating the same thing over and over. It's just accruing the damage as it happens for the particular history. And Endure can do that as well. Um, the first two categories are addressed by our CL tool, Endurica CL, which can do the infinite life and safe life approaches. If you're going to do damage tolerant, that's where you would start to use our incremental solver DT. Um, and right, and then the final category here is fail safe, and this is more a design philosophy where you say, hey, I know my part's going to fail, so let's make sure that there's safe ways to fail, right? Um, and of course, one way to do that is the implementation of a digital twin, which our tools support. Um, back to this idea of completeness. So, so we provide, in this case, 3 different software tools that have very different workflows, but each of these is aimed at certain types of problems, and together they give you a toolbox that can address just about any fatigue problem that you're going to encounter. Again, the CL workflow is for a well-defined uh, use case that you're going to repeat. You can do a safe life analysis. You can do a infinite life analysis with CL. It's just a post-process type of workflow. Um, so you would run ANSYS, and then you would run Endurica, and you'd get a fatigue contour. That's kind of an example of what it would look like to use CL. DT is our incremental solver. Um, and in the incremental solver, like I said, each day can be different, or each increment of the analysis can be different. Maybe the loads change from one increment to the next, or if you have material properties that evolve, then the material properties might change from one increment to the next. So if you're dealing with aging, if you're dealing with cyclic softening, then you would be using Endurica DT to update your material properties. And maybe you would be using the co-simulation feature, which allows Endurica to couple with ANSYS and to update the material properties throughout the analysis. Um, and then EIE, that's an acronym, stands for Efficient Interpolation Engine. We use the EIE tool when we have very lengthy road load signals. I'll show an example later on. But when we have very lengthy load signals, it's not practical to just directly run the finite element analysis to get the strain history. So we need a different tool. This is analogous to the scale and combine method that you would use in metal fatigue, but this method works for nonlinearity. And what we do is we pre-compute a set of finite element solutions, and then we interpolate among them uh, uh, to calculate our strain history. Um, Coming back again to this idea of completeness. So not only do we provide you all of the simulation capabilities that you need to model just about any fatigue problem, but we also provide a matching set of experiments, right? In the code, there are a number of different material models that handle all of the different physics that can happen in rubber. And for each of those material models, there's a corresponding experiment where you can calibrate the material parameters. So we have a testing service. We call it fatigue property mapping. You can send us samples of your material. We'll test it, and we'll get you the parameters that you can plug into our code to set up all of these different physical effects and represent those. So the two on top, the gold colored ones, that's the hyperelastic and core modules. Pretty much any fatigue analysis you're going to do is going to require that type of information. And then optionally, depending on what you're doing, you might need any of these other modules as well. So, maybe you would look at temperature effects or strain crystallization effects or aging and so on. But you would just use these blue colored modules where you need them. And so this provides a very complete set of capabilities. We're not saying that you need to do all of these things for every problem, but the options there when you need it, which is very useful. Um, so once you have these experiments and you have these simulation capabilities, the next sense in which we offer completeness is the ability to construct fairly sophisticated workflows. And this is an example of one workflow that I'll show here in a little bit. But in this workflow, we're taking road loads that we've recorded maybe at the track. Uh, we are running a finite element model of our part. We're using EIE to build what's called a map, and we're converting the loads into strain history on the finite element model, which we're then passing into our fatigue solver. Um, this is material property information that's coming into the finite element job, coming into the fatigue solver. We're computing contours of fatigue life. We're looking at failure mode. We're looking at rain flow count. And so you can build these very sophisticated workflows using the components that we've pulled together. So, one example of the safe life analysis would be this set of hoses. This is a fertilizer squeeze pump on a tractor for agricultural applications. In this case, it's a very inexpensive product, and so there's not a lot of scope to do a deep fatigue analysis, but you can check the safety factor and plot contours of safety factor. In this case, when we do the analysis, we find that for the anticipated loads, there's a safety factor of 6, which means that the product's going to be adequate to give very long service life, and because the loads are a factor of 6 below the fatigue limit. Um, that's kind of on the low end of fatigue analysis. On the high end would be cases where we're looking at road loads, like I showed in that workflow. And one of the things that we can do is we can obviously calculate fatigue life, but we can also do block cycle extraction. So if you want to use our tools to calculate simplified load cases that you could use in a test scenario for the component, that's a feature of the tool. This is for a bushing, and we took these road loads, used the Endurica code, and came up with a block cycle test that gives you really equivalent damage, roughly speaking. Right, this is the predicted damage for the road loads. This is predicted damage if you take the block cycle, and it's giving you the same failure mode and roughly the same life using this equivalent damage rule in the Endurica code. And another approach when you're using Endurica DT is you have the option to simulate sequence effects. Now, sometimes they don't matter, but sometimes they do. This is a study that was done by Sun, Gent, and Martini, where they did sequences of step up and step down load cases for a simple tension specimen. And what they showed was that Miner's rule doesn't really work always for rubber specimens. Sometimes there's a sequence effect. You can see the experimental results on the right here. Right, they predicted, Sun, Gent, and Martini predicted that a step down test is less damaging than a step up test in a filled rubber, whereas Miner's rule would have predicted those would be the same. And when we simulate those in the Endurica code, we can replicate exactly the same results that Sun, Gent, and Martini report for sequence effects. And you can see on the left is our simulated results. And so the step down test is the square, step up is the circle, and you can see that we've really kind of nailed the prediction for these sequence effects. So again, just another example of completeness in the tool set. Last example on the completeness discussion, and not going to unpack all of this, but if you're interested, at InnoTrans, which is a rail conference in Europe in September, Trelleborg talked about how they do life prediction in their rail applications. And if you follow the QR code, you're going to be able to see how the Endurica tools fit right into the Trelleborg workflows. So anyhow, so the tool set that is available now is sufficient that to do production engineering for rubber parts. So we've talked about accuracy, we've talked about completeness. The last point I want to talk about is the issue of scalability. So what do we mean by scalability? Means a couple of things. Scalability is you could talk about scalability with respect to the size of the problem, right? If we're working with road loads, a lot of times at the track, we're recording at a very, 1,000 hertz or something is our sampling rate. And so we end up with, 1 million or 10 million time steps. And so we need tools that can computationally process these very large problems in a time scale that works for engineering. So, typically you want to know that you can get a job done in a day or something, even if it's full road loads. So that's one sense of scalability. Another sense of scalability, it has more to do with the people side. So, it's about how quickly a new user who is not an expert necessarily in rubber can pick up these tools and make successful uh, calculations, without having to you know, uh, without having to be a super deep expert in rubber in particular, or in these methods. And so it's about how well it's about the documentation, it's about user friendliness, it's about having a pool of trained users, um, that if people leave your company, being able to bring somebody else in who can immediately um, pick up the workflows, and keep production moving. So that's what I mean by scalability. And what I've so this is just a slide that uh, shows our current some of our current user base. And so you can see we're every year Rubber and Plastics News puts out a issue of their you know trade press journal newspaper that lists the top, I don't know, 50 rubber companies. And every year we check the list, and we're in it. We're in the last time we checked, I think we were in it, you know, 5 or 6 of the top 10 in the world, and of course on the top 50 even quite a few more. So we're 50% in 50% of the um, application. I mentioned that as a point about scalability. Um, it means that there are a lot of people out there that know how to use these tools, and that's a good thing for not having to. It's always a very fragile situation if you're doing this in house and have a very custom thing. Then you depend on one person to have the tools work. So now going back to this idea of scalability and the compute speed, this is a benchmark that we did to look at the effect of the number of finite elements on compute resources. This is a This is a model of a tire that has lettering on the sidewall of the tire. We're just modeling and we put the Endurica logo on the sidewall of a tire. We used a global local modeling scheme, so you'll notice the tire sidewall is much more coarsely discretized. The Endurica logo has been discretized at 4 different levels. There's a coarse discretization on the left that we did with about 13,000 elements. There's a very fine discretization that we did on the right, that we did with 1.4 million finite elements. And then we did 2 in between levels, right, at 100,000 and 300,000 elements, roughly speaking. And what I've plotted in the table below is kind of the run times that we're getting for these types of problems with our code. Um, you can see that for the coarse discretization, the finite element job ran in about 1,500 seconds. So that's a little bit less than half an hour. Um, and and then the fatigue analysis on top of that really only took a very small amount of time, 0.2% of the runtime, uh, and um, and it produced about 800 megs of result files for the coarse discretization. If you look on the fine discretization, this was a much longer running job. 20,000 seconds is what? That's maybe 6 hours. I'm just dividing in my head. Something like 6 hours of runtime for that one. Uh, most of that was the finite element solve. About 2% of the time was the fatigue solve. Um, the results files obviously were huge. In that case, we had 27 gigs of results. Now this is running on a multi-threading situation. This is running with 48 threads for the Endurica solver. The Endurica solver is multi-threaded, meaning that you can run it single-threaded, or you can, distribute your job across all the different cores on your machine. So depending on your machine, depending on your license, you can, you basically run the analyses as fast as you want to. It's just a matter of distributing enough across enough CPUs to get the job to run quickly. So one dimension is number of elements. Another dimension we can look at is the number of time steps. So this is a different example. This is a transmission mount problem, and we're looking at a 3-channel road load signal here feeding into the transmission mount. On the left-hand side, you can see that we're looking at 20,000 time steps. On the right-hand side, we're looking at 500,000 time steps, and you can see the the statistics here. Notice how what I want you to notice here is that no matter how long the signal gets, the finite element runtime does not change when you're using the EIE tool at Endurica. And the reason for that is that we're not directly modeling the time history in the finite element job, right? We're just using the finite element job to create a map that we use to interpolate, right? So the interpolation becomes the part where we generate the strain history, but we just use the finite element job to explore the load space and pre-compute solution. So in all cases here, it took about 200 seconds to build the map. That map took about 93 megs of disk space. The interpolation using the EIE solver only took in the case of 20,000 time steps, we do that in 1 second or less than a second, really. For 500,000 time steps for this model, we did it in about 1 minute. And that was running on 48 threads. And now, of course, that produces huge files for the 20,000 time step problem. That was about half a gig. For the 500,000 time steps, that was 14 gigs of strain history. So you get the strain history for every time step for every element, and then when you do the fatigue analysis, you can see the runtime there. So again, for the 20,000 time steps, we're running in about 2 minutes for this benchmark. For the 500,000 time steps, we're running in about 20,000 seconds, which is, like I say, something like 6 hours for this example. So just again to give you an idea of what's the speed you can hope for. It's actually quite good. In our benchmarks, the interpolation process runs 10,000 times faster than a finite element model would run if you try to directly model the strain history here. So uh, I want to show another bushing example. In some ways, this will be similar to some of the things we've already seen, but this is basically a complete validation study that was done by GM and Tenneco for this particular SLA bushing. And so there's a picture of the mesh, there's a picture of the part. These are the material properties. So for this analysis, they actually measured the material properties of the rubber. You can see we have the hyperelastic properties here. We're using a third order Ogden model. That's our FPMH module to get the hyperelastic. We have the fatigue crack growth properties plotted here for both fully relaxing, right, R = 0, and for non-relaxing R greater than 0 conditions. This comes out of our core module, FPMC. Um, we also get our crack precursor size from this set of experiments. That's part of the core module. And so all of this becomes part of our material definition. You can see the material definition on the right here. This is just the syntax that goes to the Endurica code to set up the material. Um, we have a strain crystallization effect defined, and we've plotted out the Hay diagram here. You can see, kind of this typical crystallizing behavior. And we would normally measure this with the FPM NR module. So that's what we've done for this. Whenever I would say, when you're concerned about high accuracy, it's important to measure your own rubber. If accuracy is less of a important, the software does have a materials database, and you can, make some estimates just based on database numbers. But for the best accuracy, you really want to measure your own materials. Now, in this particular problem, the interest was in analyzing the full durability schedule for a vehicle program. And so GM has, for this particular bushing, GM has 15 different recorded histories. Each of those histories has 6 channels, right? 3 input forces, 3 input rotations. And those are all plotted out here, right? Each column is a different signal, right? So maybe one is highway driving, one is hitting a pothole, one is, city driving, braking, whatever. There's 15 of these different, or excuse me, 11. 11 of, for this particular case, there's 11 of these events or signals, and each signal has 6 channels. There's an axial, radial. There's an axial channel, there's 2 radial channels, there's a torsional moment, conical moment, and there are 2 conical moments for this bushing, and you can kind of see the history. So the point is, in this example, to simulate, and there's, if you add up all the time steps, there's about 1 million time steps on 6 channels here, and that's what we're going to use the Endurica EIE to pull the strain history out from these load histories. To do that, first we have to construct a map. And this is a plot that shows the map. Of course, when you have 6 channels, it means that your map has 6 dimensions. How do you visualize 6 dimensions? Well, you can project it onto 15 different 2-dimensional subspaces. So this is the 1, 2, the 1, 3, 1, 4, 1, 5, and so on, all the way up to the 5, 6 projections. And the red points are showing the pre-computed mapped points that we've run with the finite element solver. The blue line is the actual load history, the 1 million time steps. And you can see we don't run every single time step, but we do try to cover the entire load space. In this case, we ran 215 different finite element jobs. Each job had 11 time steps. Together, that set of jobs represented the map for doing the interpolation. And then using that, we were able to interpolate to get the strain history on the blue line for fatigue calculations. Now, in this program, it was desired to do a proper validation, and so they set up a test rig. Now, the rig did not have 6 channels. The rig only had 3 channels, so we had to kind of downsize the the road loads. So we used the Endurica tool to select which channels were the most important, and those are the ones that we carried on to the test system. And so this is kind of, so we use the axial, the radial, and the torsional moment as the retained channels. And GM and Tenneco, well, GM specifies a particular schedule. So they say, hey, signal 1 gets repeated a certain number of times, signal 2 a different number of times, and so on. Together, this schedule of events comprises the what they call one vehicle lifetime. So when we do the fatigue calculation, what we're computing is vehicle life, and obviously we want to show that the part is going to hopefully last more than one life, but maybe not be so over-engineered the part is too heavy or too costly. But like I say, so we ran the simulation again with just the 3 channels so that we could match up with the experiment. And here is the simulated failure mode and for the part. And here are the test results. So for the test, what they did was they put the bushing on the rig, they ran it to 1 life, and they validated that after 1 repeat of the schedule, there were no observable cracks on the part. You can see that in the simulation, we predicted the first crack to appear on the outside diameter. The prediction was 1.96 live. So on the so in this case the validation worked out, right? We predicted that the test, if you run 1 repeat, you should not see cracks, and that's in fact what we saw. Of course, it was desired maybe to also check the upper bound, and so we then ran some bushings to 3 lives, um, so 3 repeats of the whole schedule, and then we inspect the bushings. And in this case, we did develop cracks on the both the outside diameter and on the inside diameter. Um, again, you can see here. Here's the outside diameter. Here's the inside diameter. Both of those cracks were predicted and fit well within the life observations that we were making. So this is an example of I would say this. So this I chose this example because I think it shows accuracy, completeness, and scalability all in one example. Um, so I'll end on that point, but I started with a slide where at the beginning of all this, and I think to this day there's kind of a reputation that rubber's a hard problem, but really there are tools these days where if you know your material, if you know your loads, um, if you know your service conditions, it is very possible these days to make accurate life predictions. We've got the tools such that no matter what kind of requirement your customer is giving you, there's a really good chance you can simulate that, and you don't need to think that these are uh, you know um, uh, very extremely uh, capabilities that are out of reach for most people. We've worked really hard to make these user-friendly workflows that people can learn quickly, and scale these up to realistic problems. So, we live in a time when it's just expected that we get durability right on the first uh, product launch, and to do that, you need tools like the ones that we're showing here. So I'll go ahead and stop here, and happy to answer any questions. I think there's probably a chat or a Q&A feature if people want to ask any questions. I'm happy to answer those. Just take a look here. So.